The concept of similarity of triangles is quite often used in our daily lives to calculate the height of some tall objects or to calculate the width of a river or a bridge without using any special equipment. We can do that in our daily lives. And if you want to learn the concept of similarity of triangles, you have come to the right place. Let's jump into the video right now. Hello people. So if we talk about similarity of objects or similarity of shapes, let us look at these two squares. Do you think they are similar in shape? I think yes, they are similar in shape because all angles are the same in both the squares. And if you look at the sides, well, they are not congruent, but they are similar because the side of one square is larger than the side of other square. So one square is a little larger than the other. But yes, they are similar in shape because square on the right side just looks like an enlarged version of the square on the left side. So yes, I would say they are similar in shape. And what if I have another square like this? Is this also a similar shape? Yes, this also looks similar in shape because this is just a smaller, a scaled down version of the square on the left or on the extreme left. So any shape which is enlarged or shrunk down, they are similar. But there are some properties that we need to see when we are looking at similar shapes. What about these two circles? Do you think they are similar? Well, yes, both are round in shape, both are circles, and both have different radii, of course. So they are not congruent circles, but they are similar in shape because the radius may be a little different from the other. But what about this circle on the right side? Is that also similar? Yes, that also seems to be similar because that is just an enlarged version of the circle in the middle or a scaled down version of the circle on the left side. There are some other ways also we can look at some other shapes and see whether they are similar or not. What about these two regular pentagons that I have? Well, I call them regular because it is given that they are regular pentagons, which what is also given to us that the side of one pentagon is 2 centimeter and the side of the other pentagon is 3 centimeter, and each angle in a regular pentagon is 108 degrees. So the angles are known. So if you look at all the angles of the pentagon, all are going to be equal since it's a regular pentagon. If you look at the sides of the smaller pentagon, they are all going to be 2 centimeter each because they are equal. If you look at the larger pentagon on the right, they are all going to be 3 centimeters each. And if you look at the ratio of the sides, if you pick up any of the corresponding sides in the two pentagons, they will always be in the ratio of 2:3. Well, I've got two trapezoids also. What do you think? Are they similar in shape? Not exactly. I don't think they are similar because they do not look similar to me. This does not look like an enlarged version. This looks like a completely different trapezoid. But what if I am given the angles here that the base angles of one trapezoid is 75 degrees and 80 degrees and the other also is 75 and 80 degrees, and we know that since the trapezoids the other side is parallel, so the angles on top also of both the trapezoids will be the same, but they are still not similar because the sides are not in proportion. The height of the trapezoid on the right is almost the same as the height of the trapezoid on the left. But if you look at the width or if you look at the parallel sides, well, the one on the right is much shorter than one on the left. So these are not similar in shape. What about these two rectangles that we have? Are they similar in shape? Well, again, at first glance, I don't think they are similar in shape, but let's see what we have been given. Again, if you check in these two rectangles, all angles would amount to 90 degrees. So they are equiangular, of course. But what about the widths? What about the lengths of each of the sides? Well, look at what we have been given is that the length of the shorter side in the rectangle 1, which is on the left, is 3 centimeter, while it's 2.5 centimeter in the right rectangle. if you look at the ratio between the two sides, 3 centimeter over 2.5 centimeter, that becomes 30 over 25, or 6 is to 5. So the ratio of the shorter sides of both the rectangles to the left, from the left to the right, is 6 is to 5. What about the longer sides of each of the rectangles? So we have been given that the longer side of the rectangle on the left side is 5 centimeter, whereas the longer side on the rectangle on the right side is 8 centimeters. So the ratio is 5 is to 8. So if we looked at the ratio of the shorter sides, it was 6 is to 5, and here the ratio is 5 is to 8. So obviously, since the proportions are different, even though the angles are the same, the proportions of the sides are different. Therefore, these two rectangles are not similar in shape. They would not be called similar figures. What about these two triangles? Well, at first glance, they do look similar in shape, because the one on the right, it just looks like it has been rotated, and but they do look similar in shape. And let's see what else have we been given about these two triangles. Well, we have been given that the base angles of both the triangles is 70 degrees, and since both the base angles are the same, I would say both are isosceles triangles. And if both are isosceles triangles, what do we know about the sides? We know that the sides opposite to the equal angles are going to be equal. And what else have we been given is that one of the sides of the triangle on the left is 5 centimeters, and one of the sides of the triangle on the right is 7 centimeters, and they are one of the equal sides. So obviously the opposite sides are also going to be 5 centimeter and 7 centimeter respectively. If you look at the ratio of the sides, it is 5 is to 7. What about the base? Well, if the bases are going to be in the same ratio, then these triangles will definitely be similar to each other. And why do I say that? I say that because if two angles of both the triangles are equal, then obviously the third angle has to be equal, because in both the triangles the sum of the angles has to be 180 degrees. If we look at the bases, we have been given that the triangle on the left side, it has a base of 2.5 centimeter, whereas the other triangle, it has a base of 3.5 centimeter. Is that in the same ratio as 5 is to 7? Well, let's check. So 2.5 over 3.5, so if the decimals goes away, it becomes 25 over 35, which again dividing by 5, we get 5 is to 7. Yes, the bases are also in the ratio 5 is to 7, and if all sides are in proportion to each other and both the triangles have equal angles, then we can say that the triangles are similar. Well, the similarity of triangles can also be checked in this way, that if I took the triangle on the left side and I just tilt it over and rotate it 90 degrees like this, and then I just pick it up and put it on top of the other triangle like this, I see that one of the vertices of the triangle exactly coincides on top of the other, and the sides are also coinciding with each other. And of course they have to, because we know that these base angles of the smaller triangle is also 70 degrees. And if you see that these corresponding angles of the larger triangle and of the smaller triangles, they are both equal, then that we know that the base of the smaller triangle is parallel to the base of the larger triangle. And if you look at the sides now, in what proportion have they been divided, we know that the equal side of the smaller triangle is 5 centimeter, so obviously this has to be 5 centimeter, and if the total length is 7 centimeter, then obviously this portion has to be 2 centimeter. So see how this 7 centimeter line has been divided into the proportion 5 is to 2. And if we look at the other side also, since the line is parallel to the third side, we will see that that also has been divided in the ratio 5 is to 2. So this is not a fluke. This will always be the case, as suggested by the mathematician Thales, who showed us the basic proportionality theorem. Well, the basic proportionality theorem says that if a line connecting two sides of a triangle is parallel to the third side, then it divides the other two sides in the same ratio. And if I take any two sides of any two triangles, and if I take any two sides of a triangle and I draw a line which is parallel to the third side, and if I measure the remaining two sides, I will see that they both of those sides have been divided in the same ratio. The ratio is always going to be the same. You can draw as many triangles as you want to, and you can draw a line parallel to one of the sides, and you can measure the sides, and you can see that they'll always be the same. The other tenet of the basic proportionality theorem, or the converse of this, is that if a line divides two sides of a triangle in the same ratio, then obviously it is going to be parallel to the third side. And Thales obviously gave a proof for this, and I'm going to share the proof with you right here in this video. And let's take a triangle ABC. So let's start from the very beginning, where we took a line which is parallel to one of the sides of the triangle. So let's take the base here BC and draw a line parallel to it, and let's name that line as DE. Now if I look at the figure, the figure has been divided into two triangles now. One is the smaller triangle, which is ADE, and one is the larger triangle, which is ABC. How about finding the area of the triangle ADE? Well, we need to know the height for that, and we need to choose one base. So if I choose the base as AD, we would need to find the height, and to find the height, we will just drop a perpendicular from the vertex E to the side AD, and let's call that EN. So obviously the area of triangle ADE will be half times the base times the height. Base is AD and height is going to be EN. So the area of triangle ADE is going to be half times AD times EN. Well, the area of this triangle can also be calculated in other ways. What if we take AE as the base? Well, if we take AE as the base, then we have to drop a perpendicular from the vertex D on AE, and let's drop that perpendicular and name it DM. So obviously if we calculate the area of the same triangle ADE, then it's going to be half times the base, which is AE, times the height, which is DM. So this is, and you know that the areas of both the triangles, or both ways, since they are the area of the same triangle, they are going to be equal. Well, below the triangle, the first triangle, do you see a trapezoid where DE is parallel to BC? So there's a trapezoid that we have got, DBCE. How about drawing one of the diagonals of the trapezoid like this, BE? And we see that the trapezoid has now been divided into two triangles. One triangle is BDE. How about calculating the area of triangle BDE? Well, if we look at triangle BDE and we take BD as the base, then obviously EN is the height for that triangle, and the area of the triangle BDE will be half times DB times EN. If we draw another diagonal of the same trapezium CD like this, and we look at the triangle CDE, then taking CE as the base, the height is going to be DM, or EC as the base, the height is going to be DM. So the area of triangle CDE is going to be half times the base, which is EC, times the height, which is DM. How about taking the area of the triangle on top, ADE, and the triangle at the bottom, BDE? If we take the ratio of the areas of both the triangles ADE and BDE, what we get is something like this. I've just taken the first equation over the third equation. So the left hand side is area of triangle ADE over the area of triangle BDE, and the right hand side becomes half times AD times EN over half times DB times EN. As you see, in both the numerator and the denominator on the right hand side, half and half can cancel each other out. En and En both are the same perpendicular, so they can cancel each other out, and what we are left with on the right hand side is the ratio AD over DB. Let's take the other two triangles, the other two equations that we have, the second equation and the fourth equation, and we try and find the ratio of the areas in the same way like we did here. So that ratio is going to be half times AE times DM over half times EC over DM, and like in the earlier example, we saw half and half can get cancelled out and DM can get cancelled out, so what we are left with is only AE times EC. But don't you see that triangles BDE and triangle CDE, they should be equal in area? Well, yes, they should be equal in area because they lie between the same two parallel lines, which is DE and BC, and they have the same base, which is DE. So any two triangles or two or more triangles which lie on the same base or equal bases and they lie between the same parallel lines, they are going to always have equal areas. So here we see that the triangle area of triangle BDE and area of triangle CDE is going to be the same. And if we look at the two ratios above, then obviously they are going to be equal since the numerator is already equal, and we know that the area of triangle BDE is equal to area of triangle CDE. Then we can conclude that the right hand side is also going to be equal, which means that AD over DB will be equal to AE over EC. And do you see that AD is the side of the smaller triangle that we have? Just look at the figure. And DB is the remaining part of the larger triangle. And similarly on the right side, AE is one of the sides of the smaller triangle, and EC is the remaining part of the larger triangle. So do you see how DE, this line DE, which is parallel to one of the sides of the triangle, has divided the other two sides in exactly the same ratio? Well, the converse also can be proven in the same way, just that we start going backwards, that we divide the sides into two equal parts and then we go backwards and try and prove that the lines are parallel to each other. So if we look at the rules for similarity, well, there are different rules for different figures. So if we look at squares and circles, they are always going to be similar in shape because the radius or the side of a square, since all sides are equal, they are always going to be in some proportion to each other, and each side is going to be each side of a square is going to be proportional to the side of another square, or each radius of one circle is going to be proportional to the radius of another circle. And obviously the angles in a square, they do not change. It is always 90 degrees at each vertex, and even in a circle the angle doesn't change. It is always 360 degrees at the center. What about regular polygons? Well, like we took the example of a pentagon, we could also have taken an hexagon or a regular octagon, and we would have found that they are always similar. Each side of any regular polygon is going to be proportional or in some ratio to the side of another regular polygon having the same number of sides, and the internal angles will always be the same, so they are always going to be similar. But we saw that in case of trapezoids, the example of trapezoid or the rectangles that we took, this is not going to be work. And for irregular polygons, we should have two conditions that satisfy themselves. One of the conditions is that they should be equiangular, which means that all of the angles of the polygon or the figure have to be equal, and the other condition that has to be fulfilled is that the corresponding sides of both the figures should have the same ratio, or they should be in proportion to each other. Even if one of the conditions of these two is not satisfied, then those figures will not be deemed to be similar to each other. They will not be called similar to each other. To be similar to each other, both of these conditions have to be satisfied. But the rules of similarity for in case of triangles is slightly different because of the basic proportionality theorem that we have, and we saw that it is no fluke that it is always divided in the same ratio. So since they are always divided in the same ratio or in the same proportion, then we can just say that even if we satisfy one of the conditions that we have here, then the triangles are going to be similar, and the conditions are that they should be equiangular. Now these conditions are similar to the conditions of congruence of triangles, just that we didn't have the AAA congruence rule in the congruence of triangles, and that is because obviously having the same angles does not mean that you will have the same side lengths also. But when talking about similarity of triangles, that completely works because you can have different side lengths, but they should be in the same proportions. So if the angles are all equal to each other in both the triangles, then the triangles are going to be similar. The other condition for similarity of triangles that needs to be satisfied is that the corresponding sides of both the triangles should have the same ratio, and I mean all the three sides of each of the triangles. If they have the same ratio, then those two triangles are going to be similar to each other. If we are not given the angles, does not matter, we can just look at the ratio of the three sides, and we can say this is the SSS similarity rule for triangles, that in case the angles are not given but we see that the corresponding sides are proportional to each other, then both those triangles are going to be similar to each other. And the third rule that we have is also called the SAS rule. That means if two sides of any two triangles are in the same ratio, and if the angle between them in both the triangles is the same, then the triangles are going to be similar to each other. And through the similarity of triangles, we can like I earlier told you, we can calculate the heights of buildings, we can calculate the widths of river and we are going to take such problems in the coming video of ours, maybe in the next video or the video after that. And please do stay tuned with the channel, because in the next video we are going to cover the Pythagoras theorem, and we are going to learn two different ways to prove that why the Pythagoras theorem is correct. And one of the theories that we will use to prove that is the similarity of triangles. Well, if you like this video, it's great, and I would like to know how you like the video, and I would definitely like to hear something about your comments. So just drop into the comment section below and give a thumbs up to the video. Drop in a comment, say hello to me. I would love that, and I will definitely reply to it. And if you haven't subscribed to our channel till yet, this is the right time to it. Just click on the subscribe button here and get subscribed to it. Do not forget to click on the bell notification so that you do not miss out on any future content from us. You can have a look at these videos on the left side, like the video, share the video with your friends, and take care and God bless.